We've previously applied the particle in a box model to look at the UV-Vis spectrum of conjugated polyenes, and now using the particle in a ring, we have the analogous model system that we can use to try to gain some insights into the UV-Vis spectra of aromatics. So we have our particle in a ring model system, for which we solved for the energies being h bar squared n squared over 2mr squared, where r is our radius of our particle on this ring, which goes around some origin, and these n's are an integer, which can be anything between minus infinity up to infinity, where the absolute value being the same gives you the same energy. You have two degenerate energy levels anywhere above the ground state n equals 0. And then for our wave functions, we have that our psi n of the azimuthal angle phi, which characterizes the state in space of our particle, is equal to a normalization constant 1 over the square root of 2 pi times the complex exponential e to the I n phi. So if we want to look at the UV-Vis spectra of something like benzene, let's say we have some benzene molecule there. Okay, so what are the quantities of interest that we need? Well, first of all, we need to look at what energy level transition that we're going to be observing when we excite a particle from the highest occupied molecular orbital, the HOMO, to the lowest unoccupied molecular orbital, the LUMO. So if we draw our energy diagram here, we have n equals 0, n equals plus or minus 1, which are degenerate, n equals plus or minus 2, etc. above that. Okay, so for benzene, our pi system has 6 electrons. We have 3 pi bonds, thus 6 pi electrons. So we fill them up 1, 2, 3, 4, 5, 6. So we filled up to the n equals 1 subshell, filled up the n equals 1 shell, and if we have some photon of light that's going to be coming in here, so if we have some photon with some energy h nu coming in, then that is going to promote an electron up from our HOMO at n equals plus or minus 1 up to our LUMO at n equals plus or minus 2, giving us a final electron configuration which looks like so. We've promoted an electron up from n equals absolute value of 1 to absolute value of n equals 2. So this jump is the specific delta E that we are interested in order to calculate the energy of this photon which caused this jump here. So for different aromatics, it would depend on what the energy levels look like and what you would have to promote an electron in order to incur that quantum jump there. Okay, so we have that our delta E is going to equal the final energy minus the initial energy. So we have an electron in n equal, the absolute value of n equals 2, minus, it came from absolute value of n equals 1, so E2 minus E1. So that's going to be h bar squared is constant between them, over 2mr squared is constant between them, and then you have 2 squared minus 1 squared. And I'm also going to pull the factor of 2 pi out of the denominator of the h bar so that we can make things easier when we have to transfer this into the wavelength of the photon. So I'm going to say this equals 2 squared minus 1 squared is 4 minus 1 is 3. So we're going to have 3h squared. Then for this h bar, for each h bar we have a factor of 2 pi on the denominator, so h bar squared gives us 4 pi squared, times this 2 that's already there gives us 8 pi squared mr squared. Then we know that delta E also equals h nu, the Planck's constant times frequency of the photon, which is also hc over lambda, Planck's constant times the speed of light over the wavelength. Thus we know that the wavelength of the maximum absorption here is going to be hc over delta E. And that will be Hc times the inverse of this quantity. So let's have Hc 8 pi squared m r squared over 3 h squared. So we're going to cancel out the h in the numerator there with one of the h's in the denominator. So our final answer here for lambda is going to be that lambda max for benzene, the maximum UV-Vis absorption wavelength, is going to be 8 pi squared times mass times speed of light times the radius of the ring squared over 3 times Planck's constant. This is our absorption wavelength for the UV-Vis electronic transition of the benzene atom, the pi to pi star transition, as we would say, going from the pi bonding orbital to the pi star antibonding orbital. Okay, so what values do we use here? Well, for m, we have mass of the electron, 9.11 times 10 to the minus 31 kilograms. For speed of light, we can just use standard speed of light, 3.00 times 10 to the 8th meters per second. I'm not worrying about the fact that that's really 2.998 something something. I'm just giving you 3 sig figs there. What about for the radius? Okay, now herein comes the critical decision. So let me draw a benzene molecule there. And then our particle, we're saying, is traveling on a ring going around all of these carbon atoms there. Kind of the vertices of the nuclei of the carbon atoms, the vertices of the benzene are also on the ring there. So the critical thing to realize here is that all of these angles in benzene are equal. These are all 120 degree angles. And so if this benzene being perfectly symmetric, we can bisect all of these angles with the lines connecting them together. And then what we get are 6 equilateral triangles. So each side of one of these equilateral triangles, this distance from the origin to a vertex, that's our radius. And these being equilateral triangles, all being 60 degree angles in here, because we bisected these 120 degree angles, our r is also equal to the bond length. So R is equal to the carbon-carbon bond length, which is kind of a 1.5 bond there. And the bond length of a typical carbon atom, the typical carbon-carbon bond length in aromatics like benzene is going to be 1.38 angstroms. So if we substitute that in, that would be 1.38 times 10 to the minus 10th meters, because an angstrom is 10 to the minus 10th meters. And then we have, of course, Planck's constant, 6.626 times 10 to the minus 34th joules times second. So if you work out the units of all this, plug everything in there, you do get a unit of meters, which we can then transform to nanometers, the typical unit we want to work in for these types of things. So our theoretical lambda max here, our lambda max, which our particle in a ring model predicts for this absorption, it ends up being equal to 34 nanometers. Now that would still be in the UV range. It's kind of high energy, low wavelength for a UV-Vis transition like that. And if you compare this to experiment, you'll find that the experimental wavelength for this pi to pi star transition in benzene ends up being something like 255 nanometers. So it ends up being off by a factor of 7 here. And that's not surprising. This is a very, very crude model, but it's interesting that we can use this type of model and look at this type of transition here, given that we've said nothing about electrons, we've said nothing about nuclei. We're just assuming that you have a particle traveling around a ring like this, and you get an answer which is almost within an order of magnitude of the actual experimental answer there. So it's showing us that this general type of particle in a ring and then also particle in a box model that we're using for these linear alkenes. So just these general ideas of quantum mechanics are already getting us in the ballpark, in the region of of some of these experimental properties before we even take anything about the structure of molecules into account. So it shows that we're onto something with quantum mechanics, and that these very, very simple ideas can get you something which is not completely ridiculous and sort of on the trail for predicting these types of properties for actual molecular systems.